All right, 7.2. In 7.1, we talked about planetary motion, which is kind of ancient studies. I mean, a few hundred years ago, we're saying how planets move. 7.2, now we're using these laws to our advantage. And why? How are we going to use these laws to our advantage? Well, what's the number one thing that we need to do for telecommunications in outer space? We need satellites. How do you launch a satellite? How fast does a satellite go? How high up does it need to be above the Earth's atmosphere? All those things come into play when we're talking about satellites. So that's kind of the number one uh, application to this. So when we talk about orbit of a planet, or we can talk about the orbit of a satellite, like, okay, we're going to put a telecommunications satellite in outer space. How fast does it need to go? Where's it going to be? So we have a couple equations. But first things first, we are going to avoid air resistance. Why are we going to avoid air resistance? Well, we haven't calculated while we're on Earth, and there's no air in outer space, so it doesn't even matter. Also, though, a satellite in orbit always has the same height above Earth since it's uniform circular motion. One thing, though, that we need to point out, and we'll point it out again on the next slide, is this. I kind of have a picture here of the blue circle's Earth. If a satellite is 1,000 kilometers above Earth, you do not take the 1,000 kilometers as a height. You have to add the radius of the planet because the center of gravity is the very center of the Earth. So the whole radius is what you need to add. So a lot of times they'll tell you the satellite is X amount above Earth. You're going to have to take the X amount above Earth and add the radius of Earth together, which we'll talk about in the next slide. So the speed, how fast is something orbiting Earth or another object? Well, when we go ahead and do that, we have v is equal to the square root of capital G times the mass of Earth divided by the radius. The period, how long is it going to take to revolve around Earth or another object? The period of the satellite is equal to the square root of 2 pi times r cubed divided by capital G times the mass of the Earth. And remember, the mass of the Earth is a given, but it's 5.98 times 10 to the 24th kilograms. Right. So we take equations here, and we have a question. Right. A satellite orbits 225 kilometers above the surface. What is the satellite's orbital speed, and what is its period? All right, so what is its period? Well, let's go back. All right, we have a couple things here. We're going to use both these equations. It's asking for what is its velocity, and speed. Well, all right, so we have R total. Well, our R total is equal to the R of the planet plus the R of the satellite. It tells us it's 225 kilometers. Now, when you'll notice, this is tricky, in your book, it's going to give you the radius of the planet in meters. So the radius of the planet in meters is 6.38 times 10 to the 6th. You have to convert kilometers to meters, and when you do that, you get 225,000 or 2.25 times 10 to the 5th. Add those together, and our radius ends up being 6.605 times 10 to the 6 meters. Right. So now we are going to go ahead and we're going to solve for the velocity, right, the velocity of that planet. So remember, velocity is equal to the square root of g times the mass of Earth divided by r. Well, we go ahead and we plug everything in here. G is 6.67 times 10 to the negative 11 times the mass of Earth, 5.98 times 10 to the 24th, divided by R, which we just solved for, 6.605 times 10 to the 6th. Take that, square root it. And what we end up getting using 3 sig figs, because we had 3 in our answer, is 7,770 meters per second. All right, that's the first bit in that equation. The second bit, all right, we want to figure out the time that it takes that satellite to go around. So t of satellite is equal to the square root of 2 pi let's see here. Time of a satellite is equal to the square root of 2 pi times r cubed over g times the mass of Earth. We go ahead, we're going to plug everything in here. This is where one of those huge honky-donkey scientific calculators comes into huge play. 2 pi times 6.605 times 10 to the 6th cubed over 6.67 times 10 to the negative 11, which is g, times 5.98 times 10 to the 24th. All right. We go ahead and we plug that in. I did not do this one in advance, so give me a second to plug this into the calculator. And what we end up getting is, if I could have some Jeopardy theme music while my fat fingers plug it into the calculator. Times 2. Where's the pi button? .67 e negative 11 times 5.98 e 24. Take that and square root it. Don't forget to square root it. And we end up getting that the time of the satellite is equal to 2,130. Now, what's the unit, do you think, for period? What's our base metric unit for everything we talk about? The correct answer is seconds. So that's orbiting about every 45 minutes around the Earth. So that is, you're going to use those two equations. Couple things to finish up here. More on gravity. Acceleration due to gravity, which would be little g. The farther away from Earth's center, the acceleration of gravity becomes less. When the acceleration becomes gravity becomes 0, you experience 0g, or the feeling of weightlessness. This is kind of what astronauts feel. Gravitational field spreads out equally over Earth, so you have to think of it as all over Earth, kind of as a shell around Earth. All right, very similar to a magnetic field or electric field, which we'll talk about later in the year. So if you want to figure out a gravitational field, little g is equal to capital G times m divided by r squared. And you'll have a couple equations to use with that. We talk about different types of mass. We have inertial mass and we have gravitational mass. And really, don't get caught up in this. You're not going to use these equations too often, so you can write them down, but you'll probably use them very little in comparison to the other ones we've talked about. Inertial mass, force is equal to mass times acceleration. So if you solve for mass, mass is equal to F net divided by acceleration. And gravitational mass is that. So it's relating gravitational force between two objects that are obviously in balance. So two types of mass, inertial mass, gravitational mass. And lastly, O Einstein, how intelligent art thou? Einstein on mass. Gravity is not a force, but an effect of space itself. Mass causes space to be curved. Other bodies are accelerated because of the way they follow the curve. It deflects light. Essentially what he's saying is this. Scientists are dealing with the idea that if I have a planet here, and I have a star here giving off light really, really far away, and Earth is here. Right? What sometimes can happen is that light from this planet can travel, right, get bent around another object, and then head towards Earth. Right? Earth's assumption then is that this light is still on a straight path, and the so-called star is over here. When really, all right, objects, all right, can bend light, all right, and can kind of gravitationally follow light and kind of pull on a curve. So that's kind of a little bit about Einstein, what he thought. So gravity is not a full force, but an effect of space itself. So it affects all objects and interactions in space. So it kind of deflects light like that. If you have questions about that, we can talk about that in class. You'll have multiple problems on both equations from 7.1 and 7.2 in class tomorrow as well. So hope you had a good time. Have a good night. Thanks. Bye.